In this lecture, we'll derive the OLS formula for a linear trend line when we have one explanatory variable. So the setup is this. We have data on an explanatory variable. Let's write it like this: x1 through xn, and on a dependent variable y1 through yn. So we have a sample of n observations where we have an idea that the x variable is causing at least partially the y variable. You should know about the least squares principle. That principle tells us that if I want to fit a trend line, a linear trend line, through the scatter plot of this data, then I should pick B1 and B2 such that RSS, the residual sum of squares, is minimized. That's the least squares principle. So RSS is defined as summation EI squared, with the residuals are defined as the difference between the actual observations and the fitted values, and the fitted values are b1 plus b2 xi, so this is yi minus b1 minus b2 xi. And if I plug that into the formula for RSS, I get summation, and all the sum, they go from 1 to n in this lecture. So all these are 1 to n. I'm not going to write that out. EI squared, so that will be yi minus b1 minus b2 xi. And we're typically used to think of functions as functions depending on the x variable. But you have to keep in mind here that the variables are b1 and b2. The x's, these guys, and these guys, you just have to think about these just as constants. So what we need to do is simply we need to define a function of these two variables, b1 and b2, and that function shall be the RSS. RSS is the sum of all the squared residuals, and the residuals are given by this expression inside the parenthesis. So this is going to be my function, and it depends on the two variables b1 and b2, and it has a bunch of constants, y and I and xi's. So what we want to do is we want to minimize this function. Minimize f of b1, b2 by picking b1 and b2. This is called the least squares problem. Remember from mathematics, when we are optimizing a function of two variables, an important candidate for the solution to this problem is the point that we call the stationary point. The stationary point is the value of b1 and b2 such that both partial derivatives are zero when they are evaluated at this stationary point. So we say that b1, b2 is a stationary point if both partial derivatives, partial f, partial b1 is 0, and partial f, partial b2 is 0, when these partial derivatives are evaluated at this particular point. So the first and most important step of solving the least squares problem is to find the partial derivatives of this function f. So let's start with b1. So I need to differentiate with respect to b1 f of b1 and b2. And f of b1 and b2 is given by the sum of this expression. Keep in mind, when I want to differentiate this expression with respect to b1, all the focus is now on this one. All other symbols in this expression should be treated as constants. Just think of them as numbers when you do this partial derivative. So the first problem that we see is that we have a derivative of a sum. Fortunately, we have a nice rule for derivatives, which says that when you want to differentiate a sum, you can differentiate the elements in the sum and then just sum those derivatives. So what that means, simply speaking, is that I can move the derivative inside the summation sign. I can take the derivative of the individual elements in the sum and sum those derivatives. So I can write this as sum d db1 of this expression. So now let's focus on these derivatives. There are n of these derivatives because this is indeed a sum from 1 to n. So this is basically the derivative of some expression squared. That is, we can view this expression that we need to differentiate as a composite function. The outer function is just this square thing, and the inner function, well, that's the thing inside the parenthesis. So that's the smiley face, that's the inner function. The rule for differentiating a composite function is that I differentiate first the outer function, and the derivative of something squared is 2 times something. So that will be 2 times this inner function, represented by the smiley face, multiplied by the inner derivative. The inner derivative is simply the derivative of the inner function. And we can write that next to it. So the derivative of the inner function is the derivative of this expression here. That expression is the inner derivative. Well, this again is just a sum, so I can just differentiate each term separately. If I differentiate with respect to yi, if I differentiate yi with respect to b1, I get a 0. Just think of that as a constant. If I differentiate minus b1 with respect to b1, well, that's just a linear function, so the derivative of that is minus 1. And if I differentiate the last term, this thing here with respect to b1, it's again just the product of two constants, so its derivative is 0 as well. So the derivative of the inner function, the inner derivative, is simply minus 1. And the rule for differentiating a composite function is derivative of the outer function times the inner derivative. So we'll add that there. 2 times minus 1 is minus 2, and then we can put the smiley face back. That's the inner function, b1 minus b2 xi. So we have found the first partial derivative. The partial f partial b1 is just the sum of minus 2 times yi minus b1 minus b2 xi. And this is just a constant minus 2, and we are allowed to take constants outside summation sign. So I can write the derivative like this instead. So let's do the next one. It's very similar, but not exactly the same. Partial derivative with respect to b2 of this sum. Now the focus is here. All the other symbols should be treated as constants. We can move the derivative inside the sum and write it like this. We can again identify this as a composite function that we're differentiating. So the inner function will represent the smiley face. So if we focus on this, it is ddb2 of smiley face. Well, let's make it smile. Square. So same thing, derivative of something squared is 2 times the something. And we need to find the inner derivative. So let's do that below. ddb2 of the inner function. The inner function is the same function, like this, but now the derivative is with respect to b2. So differentiating yi with respect to b2, that's 0. Differentiating b1 with respect to b2, that's 0. Differentiating minus b2 times xi with respect to b2. Remember, this is the variable. b2 is the variable. xi is just a constant. And again, that's just a linear function, so the derivative is simply the slope, the constant in front of b2. And that's minus xi. That's the constant in front of b2. You can move it over here if you like to see that better. So the inner derivative is now minus xi, not minus 1 as was the case with respect to b1. So we need to multiply that by minus xi. Putting this smiley face back, it's minus 2xi yi minus b1 minus b2 xi. So we now also have the partial derivative with respect to b2. It's summation minus 2xi yi minus b1 minus b2 xi. Of course, we can't take this entire expression outside because the x has an I subscript, so it's not a constant over the sum, but we can take the minus 2 outside. So I can write it as minus 2 xi times yi minus b1 minus b2 xi. So let's summarize that, what we have found. We have found that the partial derivative of f with respect to b1 is minus 2 times the sum, and partial derivative of f with respect to b2 is minus 2 times this sum, where I have an xi in front of the parenthesis. Okay, so going back to where we left off with the partial derivatives, remember that a point is called a stationary point if these derivatives are 0. Well, now we have actually found these partial derivatives, so we need to set them equal to 0. So in the first case, the first partial derivative is minus 2 times summation yi minus b1 minus b2 xi. That's the partial derivative of f with respect to b1. That needs to be 0. As needs the partial derivative of f with respect to b2. That needs to be 0 as well. So the notation here is that any value of b1 and b2 that solves these two equations is a stationary point. So this is a system of equations. We actually have two equations, equation 1, equation 2, and we have two unknowns, b1 and b2. So we'll see that this is actually a linear system and it's not difficult to solve. The first thing we can do is get rid of the minus 2's. I can divide both sides by minus 2 and that's not going to change the solution. So we can get rid of these two. To find a stationary point, we need to solve this system of equations. This system of equations is actually hugely important by itself. So it's given a name. This system is called the normal equations. The normal equations for the least squares problem. This is the derivative with respect to b1, and that should be 0. This is the derivative with respect to b2, and that should be 0. So let's go ahead and solve these equations. It's just a matter of knowing your summation rules. So if we look at the first equation, we have these summation rules which says that if you sum a bunch of terms like this, you can sum each individual term. So I can write equation 1 as summation yi minus summation b1 minus summation b2 xi. I've taken the minus signs outside the sum, and that needs to be 0. This part here, this is just a sum of n constants b1. So it's b1 plus b1 plus b1 n times. So it's simply n times b1. And in this sum, this is a constant, so it can go outside. So we can write equation 1 as, well, let's do one more thing. This summation yi can be written as n times y bar. Remember, the definition of y bar as the sample mean is 1 over n summation yi. If you multiply both sides by n, you get n y bar is the summation of yi. So sum of all yi is n times y bar. So equation 1, you can write that as n y bar minus n b1 minus b2, and then I have summation xi, which I can write as n times x bar. That should be equal to 0. Equation 2 is a little bit messier because I have an xi in front. So let's start by multiplying out the parentheses in the sum. So equation 2 up here says that this is sum xi yi minus b1 xi minus b2 xi times xi, so that's xi squared. Now I can divide this up into 3 sums, so it's summation xi yi minus summation b1 xi minus summation b2 xi squared. The first sum I can't do really anything with. The second sum I have at least a constant to take outside, as I do in the third sum, so I can write this as summation xi yi minus b1 summation xi is nx bar minus b2 summation xi squared. So let's just put these two equations together. My system of equations now looks as follows. Well, first, in the equation 1, we see that we can cancel the n here. We can divide both sides by n. So equation 1 looks like this. Y bar minus b1 minus b2 x bar equal to 0. Equation 2 looks like this. Summation xi yi minus b1 n x bar minus b2 summation xi squared should be equal to 0. Here's the strategy we'll use to solve this system of equations. I am going to solve equation 1 for b1 expressed as b2. I'm going to solve for b1, then I'm going to plug that b1 into equation 2, now expressed in terms of b2, and then I'm going to solve equation 2 for b2. So equation 1 is easy to solve for b1. Can just move b1 on the other side, and we see that b1 is y bar minus b2 x bar. And that is one of the OLS formula. That's the OLS formula for b1. To get the formula for b2, take this expression and we substitute it in here in equation 2. Then equation 2 looks like this: summation xi yi minus b1 is y bar minus b2 x bar multiplied by nx bar minus b2 summation xi squared. That should be 0. Now that's an equation involving only one variable, b2, so I can solve for b2. Let's expand the parentheses. Then we have summation xi yi minus y bar plus, sorry, forgot that term, minus y bar nx bar. Then we have plus b2 nx bar squared minus b2 summation xi squared should be 0. So if I want to solve this equation, I can take these terms and move them to the right hand side. So then on the left hand side I have summation xi yi minus n y bar x bar, and on the right hand side I have to put change signs of these terms because I moved them to the other side. So I can take out b2 from both terms, so it's summation xi square minus n x bar square. You can convince yourself quite easily that this is the same thing as xi minus x bar, yi minus y bar. You get this result simply by multiplying out the parentheses in the lower expression. Similarly, you can quite easily check that this is the same thing as xi minus x bar squared. So unless this expression is not 0, then we can divide both expression by that, and then we get the OLS formula for b2, which is summation xi minus x bar yi minus y bar divided by summation xi minus x bar squared. And now we have both of the OLS formula.